the topic I want to talk about will be most likely the first more technical presentation this day, away from high-level PowerPoint down to real code. And I also saw basically that the presentation will address one of the topics, which is the issue of debugging takes too long. Good. So agenda, the first 3 points are basically kind of level setting, getting us on the same page, same language, maybe also getting used to the pictures of the tools we use for this example. The next 3 points here are basically then shown on an example. What is transaction tracing, and how can you leverage this? And then finally a conclusion about the whole topic. So let's start with the motivation. I think we heard this several times. Too much time is spent on debug problems. And why? We also heard this design get more complex. You use VIP that you don't know. You bought this from somewhere. You basically reuse, we do mainly verification at SoC level, subsystem test benches or module level test benches. You also don't know, but you want to leverage those things, but they're getting to your way when you debug things. And apart from this kind of natural things, there's also another fact that makes debugging at the moment more difficult than it should be, is there are different debug methods for design and test benches. And these things especially show up when problems you see in the design cross the border into the test bench, and you need to get an understanding of the test bench on why things behave in a certain way. And of course, the other thing on the test bench side is the infrastructure you use is sometimes not really debug friendly, getting you to the point where the problem really is. Here again, a little motivation or background. If you look at debug, there are different ways of doing debug. The first and level 0 kind of debug is you put some print statements into your code and look at your log. That's the thing most people do because they don't trust any EDA tools, and that's what that's always working. The second thing people use is waveform debug. That's naturally for design, not available in test benches. You do breakpoints, line stepping, more software kind of style, and you have some transaction debugging. If you look at these different methods that are available, we did some kind of small survey statistics. What is used by whom, and you see right now also this trend that the waveform debug or the waveform and block debug are the thing that are used the most. Transactions are rarely used up to now. Now getting into the level setting kind of slide area. This is how in the Synoposys tools wave debug look like. So you see, in essence, you will see in there modules and interfaces, static things, and they typically represent design. You see as a characteristics that information is shown over time. And there's another aspect of level setting. You also see signals on the left-hand side, which kind of represent an interface. And why do I say that? Because the other thing is, if you see those signals related to something happening over time, you have kind of a definition of a transaction. Just to basically have shown what our definition of a transaction is. The other side of the fence is basically the dynamic debug. Most often or always seen if you do test bench debugging, if you have classes there, you don't have any static information. So it's always dynamic, and you see information only at a certain point in time. So, for example, in the Synoposys tools, you see the time here. You can set a breakpoint, which is then associated with this time. You can see what are the variables, what is the content at this point in time. And you can also see the different threads that are lumping around in your system at the moment. Good. And to also show this is basically how transaction debugging looks like on the Synoposys side. Here you see in essence the different streams that are available, and on the other hand, you see kind of the content of the streams that are around. Now, before I get into code example, I want to put some structure into the whole debugging stack. We basically see this as this kind of stack. If you look at your test bench together with the design, we have some stimulus, random or directed. We have something that does some communication, decouples you from the underlying translation from things that happen here at the transaction level down to a pin level. Then we have now some interface that basically connects you to the design and decouples you or prevents you from races through clocking blocks, for example. And at the bottom you have your design. And I will basically come back to this kind of stack over and over. That's why I introduced it this way. On the other hand, now we have this example test case to illustrate how we basically implemented the transaction recording. So we use extensively abstract classes to basically capture common intent. Here, for example, register transactor and register command, which is, you can see as a TLM2 kind of pair. So you have some kind of semantic defined with this, and then you have implementations of these things for various interfaces like AHP, PCI, internal buses, so you have different implementations. If you look at, not from the structure, but from a behave, this little snippet, you will see you have a stimulus at the one hand side that wants to achieve something, and you have a driver on the other hand that is then actually doing the pin wiggling, but you have some infrastructure in between, be it TLM, or in our case it's a channel. We use our own base classes, which are similar to VMM at the moment still. And these are, in essence, the calls that are happening during your way down to execute one transaction in the stimulus side. Again, the driver is, in essence, extended from our base class, and also the channel is an extension of the command. Good. On the left-hand side, you see then the actual waveforms that this driver is generating. And now I try to get through this course of how do transactions get into the game with this infrastructure. So if you look at it from a debug perspective, you see there's something happening on the bus. You may, if you know what the interface is and how this is fed to this class, find this code here of your driver that was generating this. But if you basically follow the call stack that is natively provided, you will end up here somewhere in the channel. So you do not get, for example, here to your stimulus. The other side, of course, if you have your stimulus here and you see there's a read or write happening, but you don't know what driver is actually playing the music for this, and you look at the call stack, you will see it's also just ending somewhere in the infrastructure, but you don't get to the driver with that. And this is just an example that shows you how you, in essence, can leverage transaction recording to make your debug easier. You can apply this to interrupt service routine, register accesses, mode changes, and so on. This is just one example. Now, we have seen here this is this driver trace, to basically show you how this looks like in reality. This is, we got basically to this point that we have this get method is called in our driver here. And if you look at the call stack, you will see you will end up somewhere in the base class hell. So it doesn't help you a whole lot. You have to know now basically how the whole thing works, and then you get to where the problem is really at. The other side of the fence, or basically here's this picture you see from the class into the channel. This is what we see in this picture. From the other side, you have your stimulus here, and this does here a write. If you look at the call stack, you get also just somewhere here into base class level. And it's represented basically through this view here. If we now take the infrastructure that we've added, I will get you through how this works in concrete. Just to give you an impression, in UVM it's all magically hidden by the macros. Here you will see also some macros and maybe also some insight on that. So in essence, we have a channel command and a driver command. We will go through this flow and we concentrate on this callback here, this pre-put. And this is actually the code that we have added there. So you have these macros here where you have a stream name and a message name. These are two handles kind of to the stream. And you can also store the information with this. And all of this is basically done in the base class. So every extension is using this. And we call this here, this calling of the start macro, the start of the channel transaction. Just to show you what macros we have implemented for this, is this kind of order here. And why have we added macros? Not because we like it, but to make it in essence independent of the user or EDA specific PLI call. And you also can then of course stop the code so that there's nothing happening when you don't want to record any messages. Here you see the implementation of the macro. You see this is this PLI call here. If you want to know the correct or the complete syntax for this, you can look up the SNAC presentation that in this I captured the meaning of this PLI call. So you have this stream, you basically tell it it's a transactioner, you have a message name and a start property, not severity, and a message with it as an example. So now we got through this pre-put. We have basically opened the stream, started this sequence. Now the driver is calling this get, getting basically the command from there. Then we will get the pre-get callback called. This is how this looks like. It's not much different than the other one. The only thing is we have basically here a link then between the driver transaction and the channel transaction. So we have two transactions basically in there that we automatically link in here. And actually this linking is, I think, something that's very powerful. You can, with this, create dependency trees and support tracing through the different transactions. So once we are through this, we have basically now closed our channel transaction, started our driver transaction, created the link between both. Important is you have to have these names available so that you later can reference it. So in your user code, if you want to link things like a monitor is reporting something and later on you get an error because in your scoreboard you found a mismatch, you can link basically this error to this message that was reported by the monitor, and you can basically jump to the point where this was monitored. So you don't only get the monitor or the information there was an error, you get also a pointer to the point in time of a transaction that was actually the cause of it. So you get closer to the reality or the real problem where it was occurred. And finally, we complete the driver transaction here also in the base class with this other macro call. So we have read and write in NOAC, as you have seen in there. Now, how does this now look like in your wave if you have such infrastructure? So you see here is an ordinary waveform that is running there, and it's our internal bus that is running here. And at the bottom, you see there is our stream, and you see there is, for example, a write happening. So first of all, with this write, you see, okay, this kind of signaling here is a write, so you really don't need to understand the protocol anymore for this sake. You can immediately identify it was a write. Still, at the moment, you need to understand that this transaction is related to this kind of signals in your design. We'll come to this later, back again to this link here. So in our example, we have now the whole thing running, and we basically want now to see this link between this class, our driver here, and the stimulus. So you see here we have our stimulus. Here we have the transactions. So we find basically this blue transaction we have seen here is this driver transaction we have seen there. If you click in the wave, it will highlight this line. Then you basically can open another window, which shows you then the dependency between the transactions. So you see that this transaction is linked to these other transactions. If you select this transaction in here, you will get this other call stack here, and you come to this line, which is then, I think, shown with the next bubble. So with this infrastructure, you are now able, with a lot of clicking, get to this line where this came from. So here we have the stimulus line. Now the other thing, of course, is 5 minutes. Perfect. Since we implemented this in our base class, in our abstract base class, you extend on, of course, the intent of extending is you get some more information in there. That's the sake of doing things. But the infrastructure provided by Synoposys is actually coping with this, and we have implemented a macro for that. So we have just reads and writes basically in the bottom layer captured. But if you have additional attributes that you want to capture, like we have now some attributes and some special modes that are associated with a transaction, you can use this extend macro that is basically then capturing to this stream and the message name here, these additional attributes. So you basically can extend and put additional information in there if you need, and normally that's needed. Good. One thing that was added with the last release was basically the ability to trace from your signals that you have in the design, I think it's this one here, through, in our case, the program block into the classes. So you have, with the last release, the ability to trace like you're used to, an edge changing, like a read-write. You do a find twice driver, and you get, with this new update, down into your class code. So you see in the class, okay, in here, this signal, this interface was driven. So you got basically this link also established. So we have seen we have now a link from here to here, and a link from here to here. But what's missing is, in essence, the link between this and this here. So you still have to do this manually, and you have to do a lot of clicking. That gets me to the conclusion already. So what we see is basically this transaction recording helps to fill the gap between waveform and software debugging, because it allows you to trace from the normal design debug handling into the test bench in a similar way. You may have heard it in my comments, the implementation on the tools need to be improved from my perspective. I don't want to use a different way of seeing how the things relate. If not needed, I just want to do it like a normal trace driver and say, okay, who basically was the parent of that by double clicking on it or something like that, and not opening another window. It sometimes is more confusing than helping. The other thing we have seen, since we do not use UVM, and the question is if the things you really want to do are designed really ground level things or easily handleable in UVM as well, is that it's possible to add this into an existing environment to enhance the debugging performance. But, and that's the other thing, and also one of the requests I made to Synoposys especially already, is there is this link missing between this waveform debugging and the transaction debugging. So I want to basically click on a signal, and I want to get through the transactions up to the line that basically issued the whole thing without 25 clickings in the middle. Because this is what we see often happening. The designer is looking at a problem, and as soon as it hits the test bench boundary, he's lost. he's always asking where is this coming from, why is this happening, and then he needs always the test bench expert who basically can explain this is this class going there, this channel, and probably it's this line. Set a breakpoint here and build in rerun. But having this feature available would help to bridge this gap easier or make the designer capable of handling this himself. Good. That was basically my presentation.
Are there any questions? Debug is stated by many people to be one of the biggest challenges, and I personally think one of the areas where there's been lack of innovation over the past 10, 15 years. It's important to us to have a presentation on debug, so thank you to Joachim for that. I have one question actually. Have you measured the time improvement in debug that you think you get from this, or do you have a gut feel?
Yeah, I see it always. I have a gut feeling that it's faster, especially the transaction recording gives you an immediate feedback on what the test bench thinks it happened versus what you see. So you can look into your streams and see what registers got accessed, which didn't. I don't look at the waveforms. I see what ISRs were exercised, what stimulus did run. So this helps immediately to get me into the static mode from design versus I have to set a breakpoint to figure out was this register accessed, or I need to figure out what address is this, and because it's not the whole thing, you have to extend it and so on. So it helps a lot. As usual, it would be good to put up metrics so that you can capture state of the art at the moment and see what's afterwards. But this also requires that a whole team is actually contributing to this. And that's always difficult because in most cases people fear like watched rather than improved with such actions.
Thank you, Joachim.